Hey kiddos, happy lesson 9. Today is the last lesson for IB Physics 1-2. Today's goals are to finish talking about electric potential and electric potential difference and how we can use that information to describe the motion of charged particles. In addition, we'll talk about reviewing for our field forces test that will happen next class during our final class meeting, and there'll be some time for review. So let's get going, and we'll start off with an example. Okay, if you remember when last we met, we were looking at electric potential, also known as voltage. So the positive plate is always thought of as high voltage, right? There, a positive test charge would have high potential energy. And then down closer to the negative plate, that's a region where a charged positive test particle would have low potential energy, and so it's represented with low voltage. At that negative plate, a positive test charge would have no more potential energy. There'd be nowhere else it could go, so the electric potential energy would be 0 and the voltage is 0. Okay, so remember, voltage as a concept is not just electric potential energy, but it's a ratio of electric potential energy per unit charge. It's in joules per coulomb, also known as volts, abbreviated with a capital V. Okay, so the electric potential or voltage just kind of tells us how much potential energy per coulomb a charge would have. And you can see up high is high potential, and as you get lower, you've got lower potential, just like a basketball would have lower potential energy as it got closer to the ground. If we wanted to, we could represent regions of different voltage with lines that we could call equipotential lines, right? So all across these lines, a charge anywhere along one of these green lines would have the same potential, okay? And they're evenly spaced, right? So voltage of 1, 2, 3, 4, 5, 6, 7, 8, 9, and then that positive plate would be a voltage of 10. Okay, so evenly spaced between the two charged plates, where the negative plate has a voltage of 0. Okay, now if a charged particle goes from one voltage to another, right, goes from one voltage to another, its electric potential energy will change. And we know conceptually a change in voltage or a change in energy means work is being done. Okay, so work is being done per unit charge. I want to add one more thing before we do our example. Okay, so we know change, actually I don't want green, pink, obviously. Okay, change in voltage is equal to the amount of work done per unit charge. And we know from our study of energy, work, and power that work is a change in kinetic energy, right, per unit charge. Now, what we'll assume is if we have a charged particle that's right here, we're assuming that it's going to be starting out from rest, and the work that's done by the electrostatic force between it and the charged plate is speeding up that charged particle, is changing its kinetic energy, right? So here we've got kinetic energy. Changing kinetic energy is kinetic energy final minus kinetic energy initial per unit charge, right? And then the final kinetic energy is just like when we were talking about the motion of macro objects like, I don't know, rockets, balls, all of that sort of stuff. we consider the kinetic energy, right? What that object will have the instant before it slams into that negative plate, or instant it slams into the ground. So the final kinetic energy won't be 0. We're assuming the initial kinetic energy is 0 and that our object is starting from rest. So we could write this as, instead of kinetic energy final, how do we write kinetic energy? 1/2 mv squared per unit charge. Okay, so we get change in voltage time equals 1/2 mv squared per unit charge, right? Then conceptually, what is a voltage doing? If we put a charge in a region where there's some difference in potential between it and another charged object, what's going to be happening, right? The kinetic energy is changing. Voltages speed up or slow down particles. They change their speed. Okay, do you hear that? Voltages change a particle's speed. Okay, please box that, star it, do whatever you need to do. That's conceptually one of the most important things. Okay. Electric fields exert forces. Voltages change a particle's speed. One more time. Voltages change a particle's speed. Okay. Now, we can take this equation and we'll rearrange it in its most common form, right? Potential difference times charge. Okay, so these aren't 3 variables. If you want to put parentheses around one or both of them, please do. Potential difference times the charge of the particle that is existing or moving between those 2 potentials is having its kinetic energy changed, right? So this is one of those things I always tell my students, go ahead and get this tattooed on the inside of your arm or something, like right kind of on your wrist. Someday I'll show up with it tattooed on my arm. No one will be surprised. Okay, we're going to see this equation over and over and over and over and over and over again in this unit, in circuits unit, in magnetism unit, when we study quantum, nuclear, and particle physics. It's going to be an equation you're going to want to know and love. Commit it to your heart. Okay, so if a charge is moving through a potential difference, its kinetic energy is changing. Okay, so with that information, let's go ahead and try this problem. So how much work is done on a proton to move it from the positive to the negative plate? All right, so here we've got our red plate. It's positive. We've got our black plate. It's negative. Remember, the positive plate is always high potential, and the negative plate is low potential. And we can go ahead and assume that low potential is equal to 0 volts. And if the potential difference, right, they're saying this is the potential difference between the 2 plates is 250 volts. If the negative plate is 0 volts, then that means the high potential or positive plate has a voltage of 250 volts. All right, so they're asking how much work is done on a proton. Pause. Proton has a charge. The charge of a proton is equal to positive elementary charge, which is the charge of an electron. It's also the charge of a proton, and it's 1.6 times 10 to the minus 19 coulombs. All right, and then the mass of a proton is easily Googled. It's also in an IB physics data booklet that you guys will get next year. It has a mass of 1.67 times 10 to the minus 27 kilograms. All right. So with that information, now that we know what the deal is with the proton, we're moving it from the positive to the negative plate, which means it will move through a potential difference of 250 volts. Okay, how much work? So we're trying to solve for work. Okay, well, we know potential difference equals work done per unit charge, right? Which means work is charge times potential difference. Okay, so that means work is charge, 1.6 times 10 to the minus 19, times potential difference, 250 volts. And that is equal to 4 times 10 to the minus 17 joules. Okay, it's not very much energy, is it? But it's a little tiny bit of energy, but it's the amount of energy gained by a little tiny particle. So when I ask how fast is it going when it hits the negative plate starting from rest, right, all of this other stuff up here still applies, right? This is how much work is done. And what we want to know is we've got V initial equals 0, V final is what we're looking for. And so the equation that we derived up here, this was assuming that the initial velocity was 0. Okay, so we would solve for the final velocity knowing that work is equal to 1/2 mv squared. So the work is 4 times 10 to the minus 17 joules equals 1/2. Mass of the proton is 1.67 times 10 to the minus 27 kilograms, and we're looking for V. Okay, and we won't want to forget to square root our answer. And it turns out that little tiny particle that had a little tiny change in its energy, it was enough energy to speed up that particle to 220,000 meters per second. It doesn't take very much energy to speed up a little tiny particle a whole heck of a lot. All right, so this type of problem here is very, very common in terms of what you'll be asked to do in terms of problem solving for parallel plates and potential differences. Okay. So one more summary here. What causes a potential difference or voltage? It's a separation of charge. So if you've got a charge in one place and a charge in another place, right, there will be a force exerted between the charges, and that causes a change in motion. Okay, and a charge will move from one potential energy to another, and from one voltage to another, and have their kinetic energy changed. All right, one last thing that I would like to take a look at is potential difference due to point charges, and this isn't nearly as common in terms of problem solving for the IB curriculum, but I want to include it for the sake of completeness. All right, so let's say we've got a big positive charge here. What direction would the electric field point? Well, remember, place a small positive test charge. And what would it do in a region outside of a large positive charge? It would be repelled. Okay, so you try and draw evenly spaced electric field lines. indicating that a positive test charge would be repelled in that